Welcome back to our video lecture on fluid mechanics and machinery. So in the previous video we saw the units and dimensions, basic introduction to the fluid mechanics, and we saw some fluid properties. So the continuation of the fluid properties we'll be seeing in this lecture. So let's continue. Now we'll see about viscosity. So viscosity is the property of fluid which offers resistance to the movement of one layer over adjacent another layer of fluid. So while a fluid is flowing through a body, there will be series of the fluid particles flow in layers, and while flowing, the fluid above offers some resistance to the fluid below. So the adjacent fluid layers offers resistance to each other. Such property of fluid is known as viscosity. So let's take a system here. When we take two layers of fluid which is at a distance of dy apart, they move over the other at different velocity. The velocity is different at the different layers. Let's say the velocity of one layer is u and the other layer is u plus du. Now this viscosity and relative velocity causes a shear force to act between these fluid layers. The top layer causes a shear stress on the lower layer, and the lower layer causes a shear stress on the adjacent top layer. So this stress is proportional. That is, the shear stress which is produced is proportional to the rate of change of velocity with respect to y. So we can tell it mathematically as shear stress is usually denoted as tau. So tau is directly proportional to du by dy. So du is the relative velocity and dy is the distance between them. Now to remove this proportion, we introduce a proportionality constant which is mu. And this mu is called constant of proportionality, or also known as coefficient of dynamic viscosity, or simply viscosity. Now du by dy represent rate of shear strain or rate of shear deformation, or it is also known as velocity gradient. Now unit of viscosity. So the MKS unit of viscosity is kilogram force second per meter square. CGS unit is dyne second per centimeter square, or it is also known as poise. So in most of the problems you could see the unit poise, and the relation between and we come for SI unit, it is Newton second per meter square or Pascal second. So you need to convert this CGS unit into SI unit, and the conversion is that 1 poise is equal to 1 by 10 Newton second per meter square. So keep it in mind that 1 poise is 1 by 10 Newton second per meter square. So it will be useful in handling the problems. Now kinematic viscosity. So it is a ratio between dynamic viscosity and the density of a fluid. So it is denoted by nu. So kinematic viscosity nu is equal to mu by rho, the dynamic viscosity by the density of the fluid. So, and we can classify the fluids based on this Newtonian viscosity, Newton's law of viscosity. So based on this viscosity, the fluids which obey this proportional law is called as Newtonian fluids, and the fluids which doesn't support or obey this law are non-Newtonian fluids. So let's see this in detail. An ideal fluid. What is an ideal fluid? An ideal fluid is a fluid which is incompressible and has no viscosity. That means while flowing there will be no shear stress produced between adjacent layer. Such a fluid is called ideal fluid, and it generally doesn't exist, since practically seeing every fluid exerts some shear stress on the adjacent layer, that is, it has some little viscosity. So an ideal real fluid possesses viscosity. So generally all fluids in actual practice are real fluids. The fluid which obeys this Newton's law of proportionality, that is Newton's law of viscosity, is Newtonian fluid, and that which doesn't obey this Newtonian law of viscosity is non-Newtonian fluid. And an ideal plastic fluid where shear stress is more than the yield value, and shear stress is proportional to the rate of shear strain or that velocity gradient. Okay, the gradient is known as ideal plastic fluid. So you could see the shear stress to velocity gradient diagram here, by which we have classified the types of fluids. So let's see a problem. If the velocity distribution over a plate is given by u equal to 2 by 3y minus y square, in which u is the velocity in meter per second at a distance y meter above the plate, determine the shear stress at y equal to 0 and y equal to 0.15 meters. Take dynamic viscosity of fluid as 8.63 poises. Now they have given u, and we know the Newton law of viscosity, tau is equal to mu into du by dy. So u is given, so we can find the differential value, that is du by dy we can find, and that's the first step. And by substituting at y equal to 0 and y equal to 0.5, you could get the two values, du by dy at the rate of y equal to 0 and du by dy at the rate of y equal to 0.5. So we got the two values. Now they have also given the value of mu, and it is in poises. So let's convert this value in terms of SI unit. So 8.63 poises can be converted as 8.63 by 10 Newton second per meter square, that is 0.863 Newton second per meter square. Now we can substitute these values in the Newton's law of viscosity, that is tau is equal to mu into du by dy, so that we can obtain the shear stress at y equal to 0 and y equal to 0.5 by substituting the corresponding values of du by dy. So by substituting that, we have got 0.5756 Newton per meter square at y equal to 0, and at y equal to 0.5 the tau value is 0.3167 Newton per meter square. That's a simple problem. It's asked in 2 marks, so go through it. Next is compressibility and bulk modulus. We all know that bulk modulus is the ratio of compressive stress to the volumetric strain, and this compressibility is the reciprocal of bulk modulus. So let's see the mathematical relation. So consider a closed cylinder. So it has a piston, okay, and a fluid is inside. Let V be the volume of gas or the fluid which is closed in this cylinder, and P be the pressure of the gas when the volume is V. And the pressure is increased to P plus dP, that is we increase the pressure by a certain value, a small value dP, and by application of this pressure, this volume decreases to dV, okay, that is V minus dV. So increase in pressure is dP, decrease in volume is dV, and volumetric strain is change in volume by original volume. The change in volume is dV and the original volume is V, and since that is a decrease in volume, we denote it as minus V. So volumetric strain is minus dV by V. Now bulk modulus is represented by capital K, and it is equal to increase of pressure by volumetric strain. So increase of pressure is dP and the volumetric strain is dV by V, which is of negative sign. So we get the final value minus dP by dV into V. So this is bulk modulus, and the reciprocal of bulk modulus is compressibility. So compressibility is 1 by K. So let's see some problem here. So determine the bulk modulus of elasticity of fluid or liquid if the pressure of liquid is increased from 70 Newton per centimeter square to 130 Newton per centimeter square. The volume of the liquid decreases by 0.15%. Now the initial pressure here is 70 Newton per centimeter square, and we have increased the pressure, and the final pressure is 130 Newton per centimeter square. We need to find dP, that is increase in pressure, which is 130 minus 70, and we get 60 Newton per centimeter square. Also, we have to find the change in, that is volumetric strain, and we know it's given that the volume of liquid decreases by 0.15%. That is, it decreases 0.15% of original. If we consider original volume as 100, the change in volume is 0.15. So that is 0.15 by 100. Now, according to the formula, we know dP by minus dV by V. So dP is 60 and dV by V is 0.15 by 100. So we'll get 4 into 10 power 4 Newton per centimeter square. Oh, it's a simple problem. So next we'll see about vapor pressure. So we all know the change of liquid from liquid state to gaseous state is known as vaporization. So, and the vaporization occurs because of continuous escape of molecules through the free liquid surface, and it also depends upon the prevailing pressure and temperature conditions. So, consider a liquid. Let us say it's a water which is confined in a closed vessel. So, let the temperature of liquid be 20 degrees Celsius and the pressure is atmospheric pressure. Now, the liquid will vaporize at 100 degrees Celsius as it's the boiling point of the liquid, and when the vaporization takes place, the molecule escapes from the free surface of the liquid. Now, the vapor molecules gets accumulated in the top layer, that is near the top layer of the liquid surface, and it occurs as a layer between the gaseous phase, that is gas, and the liquid. So this accumulated vapor, the vapors which has escaped from the surface of the liquid, exert some amount of pressure to this liquid, and it is known as vapor pressure. The pressure exerted by the escaped liquid vapors on the liquid surface is known as vapor pressure of the liquid, and this is the pressure at which the liquid is converted into vapors. So, vapor pressure is very much essential to know the vaporization range, at what temperature or what pressure the vaporization happens. So, normally for water we see that at 100 degrees Celsius it changes into vapor. So, if we are having the temperature as 20 degrees Celsius, and if suppose we change the pressure, whether can we alter the boiling point? Surely we can alter the boiling point. So, if the pressure is brought below the vapor pressure, or the pressure is vapor pressure or less than the vapor pressure, the boiling point starts however temperature it is. It may be, if the water is in 20 degrees Celsius and the pressure is decreased below vapor pressure, automatically the liquid starts boiling. So, vapor pressure is highly significant. We should know the vapor pressure of various liquids. Next is surface tension and capillarity. So, surface tension is defined as the tensile force acting on a surface of the liquid which is in contact with a gas or a surface between two immiscible liquids, such that the contact surface behaves like a membrane under tension. The magnitude of this force per unit length of free surface will have the same value as surface energy per unit area. So, it is denoted by the Greek letter sigma. In MKS unit, it is expressed in kilogram force per meter, while SI unit is Newton per meter. So, let's see about the surface tension in some more detail. So, consider, see this picture. So, consider three molecules of a liquid. Right. Here the molecule A is deeply immersed somewhere in middle, and it is equally attracted by in all direction by the adjacent molecules. and we can see that B is in the upper surface partially, that is it's near the upper surface, and here it is not equally attracted in all direction. It has some vacant space in the upper free surface. Okay, and C is it has the midpoint of CG is in coincide with the free surface, and hence it partially attracted in all direction below, while upward it is not attracted. So there is an net downward force, and it's unbalanced, so there is a net downward force acting on this molecules B and C. So however this we can see that all the molecules which are in the top surface, the upper surface of the liquid, experience a downward force. So due to this downward force, the upward free surface, that is the surface of the liquid, acts like a membrane layer which is in tension. So this downward force tends to move the molecules downward. However, it can't move downward due to the adjacent molecules, and it stretches out like a little membrane under tension. So that is called capillary surface tension. Now, surface tension on a liquid droplet. So consider a spherical liquid droplet, okay, and its radius is r. So on the entire surface, this surface tension acts on the surface. So on the entire surface, we get the surface tension. So let sigma be the surface tension and P be the pressure intensity inside the droplet, and D is diameter of the droplets. So let's cut this droplet into two. Imagine that we are cutting it into two halves. The force acting on one half, take the left half, and let's say, and this force will be tensile force due to surface tension. This surface tension acts circumferentially on the cut portion. So to get the tensile force, we can multiply this sigma, that is surface tension, into the circumferential area, which is pi d. Okay. Next, the next force which acts on is the pressure force on the area, pi d square by 4. That is the whole circle. The pressure force acts, that is pi d square by 4. And to get this pressure force, we will multiply the pressure into area, and we get the pressure force P pi d square by 4. Now at equilibrium, these two forces are equal and opposite and are balanced. So we get P pi d square by 4 is equal to sigma into pi d. And further, by simplification, we get P is 4 sigma by d for a liquid droplet. So this equation shows that the decrease of diameter of the droplet, pressure intensity also drops inside. So the pressure intensity inside the liquid which will increase. Now for a hollow bubble, that is let us say take a soap bubble. It has air in two sides, and it is surrounded by a thin film of bubble. Okay, so thus the two surfaces are subjected to surface tension. The top surface also exerts a surface tension, and bottom also, inside also exerts a surface tension. So the pressure force is the same, while the surface tension is twice. Since it acts on the two sides, we will multiply by 2 times. For a hollow bubble, it's twice sigma pi d, and so the resultant answer that we get final pressure intensity is 8 sigma d. Now, surface tension in a liquid jet. So liquid jet considers this, it will be mostly cylindrical shape if we take a section. Now let the diameter be d and the length will be L. So pressure intensity we consider it as P, and the surface tension let it be sigma. So let's take a semi jet, that is we cut the jet into halves, and one half we are taking for consideration. So the pressure acts on the area of the semi jet. So P into length into this diameter. Okay, the diameter we are taking. Now the pressure force acts on the surface, the outward surface. So it is sigma into 2L. So equating this both, we get P is equal to 2 sigma L by LD, and further simplification we get 2 sigma by D. So the pressure, let's see a problem. The pressure outside the droplet of water of diameter 0.04 mm is 10.32 Newton per centimeter square atmospheric pressure. Calculate the pressure within the droplet if surface tension is given as 0.0725 Newton per meter of water. So they have given the diameter of the droplet, and pressure also they have given, and surface tension is provided. Now they ask the pressure intensity, that is P value they are asking, pressure force. So it's a droplet of water, so the pressure force is given as P is equal to 4 sigma by D. So substituting the values, we get a 7,250 Newton per meter square. In terms of centimeter square, if we convert, we get 0.725. Now pressure inside the droplet is this pressure intensity plus pressure outside the droplet. Now, so the sum of those two gets 11.045. Next is capillarity. So capillarity is the phenomena of rise or fall of a liquid surface in a small tube relative to the adjacent general level of a liquid when tube is held vertically in the liquid. So suppose we are taking a small tube, glass tube, and dipping it inside a beaker of water. So when you do this, due to some property, the water rises in this small tube. So such the phenomenon is called capillarity. So due to capillarity, the water rises in this small tube, and this rise is called capillary rise. So the rise of liquid surface is known as capillary rise, while fall of the liquid surface is known as capillary depression. So it is expressed in terms of centimeter of millimeter of the liquid. Its value depends on the specific weight of the liquid, diameter of the tube, and surface tension of the liquid. So let's see the expression for the capillary rise. So as I said earlier, let's consider a small glass tube of diameter D, and we are inserting inside a liquid, say water. Now the liquid will rise in the tube above the level of the liquid in beaker. So let h be the height of the liquid in the tube. Okay, the rise be h. Under the state of equilibrium, the weight of the liquid of height h is balanced by the force at the surface of the liquid in the tube. But force at the surface of the liquid in the tube is due to surface tension. Okay, so this height is balanced by the force on the surface of liquid, which is surface tension, and let sigma be the surface tension and theta be the angle of contact between liquid and the glass tube as shown in the figure. Okay, this the depression gives some angle, and that be the theta. Now weight of the liquid in height h in the tube is area of the tube, that is volume of the tube, into rho g. Okay, so that is nothing but volume into unit weight. That is pi by 4 d square into h rho g. Rho is the density. Now vertical component of surface tension force is sigma into circumference cos theta. Since it is acting inclined direction, we are resolving into two direction, and the vertical component we get sigma pi d cos theta. So in order to obtain equilibrium, these two forces should be equal, and while equating we get the h value as 4 sigma by rho gd. Similarly, we can get the expression for capillary fall as h equal to 4 sigma cos theta by rho gd. So value of theta for mercury and glass tube is 128 degree. Now let's see a problem. Calculate the capillary rise in a glass tube of 2.5 mm diameter when immersed vertically in water and in mercury. Take the surface tension sigma as 0.0725 Newton per meter for water and sigma as 0.52 Newton per meter for mercury in contact with air. The specific gravity of mercury is given as 13.6 and angle of contact is 130 degree. Okay, diameter of tube is given surface tension is given for both water and mercury, and specific gravity of mercury is known, 13.6. Density is also given. So from the specific weight we get the specific gravity. We can obtain the density by multiplying into the density of water. Now capillary rise of water. So for water theta is 0, and using the equation which we saw earlier, H is equal to 4 sigma by rho GD, and for sigma of water we have to substitute, and pi of rho of water into gravity into the diameter. So we get the answer. For mercury, it is depression. When we insert some tube in a mercury, the level in the tube falls below the water surface level. So hence it is fall, and use the formula of capillary fall. And to denote the fall, we represent it in negative sign. Okay. So by substituting the given values, you can easily obtain the answers. Okay, that's all for the properties of fluid. We have covered all, and just go through everything once more, and let's end this video. Thank you.